Alright, here we are. It is June 9th, 2016, and let's begin. Last lecture of the week. Alright, so this is the first problem we're going to go over from material from yesterday. Let's see. So cable AC, so we have another radio antenna here with 3 guide wires. We have cable AC, so from here to here is 70 feet long, and the tension in that cable is 5,250 pounds. Determine A, the X, Y, and Z components of the force exerted by the cable on the anchor C, and the angles theta X, theta Y, theta Z, defining the direction of that force. Okay, so how might we do this? Well, first of all, we do know we know that cable AC is 70 feet long, so that will be useful. So we could try to do this through a raw vector method where we try to get the coordinates of C and the coordinates of A, and then just directly calculate the unit vector, etc. But I think that's going to be a bit too problematic in this case. That's going to involve a lot of trigonometry and not really going to be the most ideal solution. So instead, I'm going to use the method we looked at previously yesterday of the 2 triangles, breaking this down into 2 triangles. So first, I'm going to draw a triangle. ACO. So consider triangle ACO, or CAO, or whatever you want to call it, with A at the top here, O at the origin, and C at this point here. Now, let's see. So what do we know? We know that this here is, well, actually, we could look at it that way. Yes, this will work. I believe, actually, it's 70 feet long. And actually, this is a little bit tricky when I think about this. Does it give us the vertical angle here? Let's see. We know it's 70 feet long. Cable AC is 70 feet long. Oh, no, this actually, never mind. This will be fine. This will be fine. See, all we have to do is we just say this is 70 feet long. We're not going to need the angles. This is 56 feet. And then we can use the Pythagorean theorem. And this should say, that looks too much like degree sign. So I'm going to erase that and put a feet sign here. That is 70 feet long. Okay, so the hypotenuse of this triangle is 70 feet long and the height is 56 feet. And I'm going to recognize that this is proportional to the following triangle, the following force triangle.
Is there something you should look at when determining whether you use the triangle method or
the question is there something we should look at when determining whether to use a triangle method or not, or the coordinate method? Largely it just comes down to experience. You could do it either way. But if I already, basically I would be inclined to use the coordinate method if I already know the coordinates. In this case, I don't know what this side length is. I don't know what this coordinate is. I don't really know either these X or the Z coordinates of point C. I do know all the coordinates of point A. I know that it's at 0, 56, 0, but that's all I know about it. I don't know the coordinates for point C. I could solve for it using trigonometry, but I think this might be a little bit simpler. Okay, so let's consider these forces. I'm going to call this, let's just say, for simplicity, I'll just call this F. Again, it's going to be completely arbitrary what you call these things. I'm going to call this force component F sub y, and this Fxy. And that is to indicate that this, oh, not xy, xz. Fxz, thank you. And the reason that was incorrect, the reason this should be fxz is because this is in the xz plane. So the reason I'm using this compound notation with both the x and the z there again is because it's not directly along the x-axis, it's not directly along the y-axis. That component lies somewhere along the xz plane. I'll have to construct a second triangle later on to break that into its x and its z components. Okay, so first I'm going to use the Pythagorean theorem to solve for length OC. And this is simply the square root of 70 squared minus 56 squared. And this comes to, yeah, it comes to the answer.
42.
Yeah, the answer. Life, the universe, and everything? No? Okay, anyway.
I'm just seeing the Chinese, it was like the Chinese symbol for life or something. Looks like a 4 and a 2.
Okay. Anyway, well now we have the now we have the dimensions of our actual physical triangle, and I do know that F here has a magnitude of 5,250 pounds. And now I can simply use proportional triangles to solve for all of the other forces. So let's see here. I will know that Fy is going to be, if you work through your proportional triangles, you will see that Fy is going to be equal to 5,250 pounds times 56 over 70. Yep, no, sine actually. So 5,250 times 56 over 70. And that comes to 4,200 pounds. And Fxz is going to be 5,250 pounds times 42 over 70. And that comes to 3,150 pounds. 3,150 pounds. Next, I need to break Fxz into its x and z components. So I'm going to draw another triangle, this time on the xz plane. So I'm going to draw essentially this triangle here on the xz plane. So for convenience, maybe I'll just call this point, we have, let's see, we have A, B, C, D, O. Let me just call this point E. It's completely arbitrary what I call this. It does not matter whatsoever. So I'm drawing another triangle now, a triangle in the xz plane. So I can have point E. Actually, no, I want to make that the origin.
If you connect it to the x plane, you can just use sine and cosine.
The reason I'm doing it like this is because they had the 50 degrees there. I could just do it the other way, but that works. We could do this multiple ways. So this is 50 degrees. And I'm going to have, let's see, I'm going to have E. No, I'm sorry, I keep doing that. This is O. O, you gotta be able to sort of visualize this in 3 dimensions. E and C. Now, along the, I'm not going to bother writing down dimensions because I already have the angle. I'm instead going to write this as a force triangle directly here. However, actually, you know what? I might instead switch these arrows around. Let's see, because I want my force, I think I drew the arrows the wrong way. I want my arrow pointing toward the origin, because the force is going to be going toward the origin. So let me just resketch this triangle really quickly. So here, the overall force will be going towards the origin like this, and which means this one will be going down like this, and this one must be going like this. I get this one because the overall force is going towards the origin here in this plane. Like that. And this is going to be F, X, Z. This is F, let's see, from E to O will definitely be my Fx. And from C to E will definitely be my, actually no, this will be my Fz. Yeah, this will be my Fz. From E to O will be my Fz. And from C to E will be my Fx. So then I can simply say Fx is Fxz times, let's see, well, I'm not going to use a parentheses, I'm just going to use the cosine, or actually in this case the sine, times the sine of 50 degrees equals 3,150 times the sine of 50 degrees equals 2,413. And then Fz is going to be Fxz. Should I add a negative? Yeah, I believe so. Thank you. That would make sense. Thank you. We got to be careful on that. Negative. The downside of this method with the triangles within triangles is that you do need to be very mindful of your negatives. It doesn't handle it automatically for you like the cross product, or sorry, like the simple vector method would. So cosine of 50 degrees. And let's see, is this going to be, this is also going to be negative, isn't it? Because it's going to be in the negative z direction. So I'm going to have negative 3,150 times the cosine of 50 degrees, negative 3,150 times the cosine of 50 is negative 2,025 pounds. And that's how you get your force components. So that's part A. And I don't feel a need to work through part B, because B is just a fairly straightforward application of the cosine formulas. Those are trivial. Look at the force here. See, at point C, this is in, look here. The force along line CA is tension. It is clearly going to be pulling up on the anchor. The anchor is pulling down on the cable, but then the cable is pulling up on the anchor. So it's pulling up and toward the peak. And if you look at the direction of that vector, that is in the negative x direction, say along here, it's in the negative z direction, and it's in the positive y direction. So that's fundamentally where these signs are coming from, where the positives and negatives are coming from, is looking at the system directly and sort of eyeballing and say, okay, this clearly has to be in this direction, and just slapping a negative on or positive on as required. And B, apply formula cosine theta x equals fx over f, etc. Okay. Questions? Yes.
Okay. Now I understand the negative at the end, but you got the negative from the sine and cosine of 50 degrees, or is that just from the 3,150 pounds?
Neither. It's looking at the system and figuring out where I need to apply a negative.
Okay.
The question was whether the negative came from the sine or cosine or from the 3,150, and the answer is neither. Okay, 2.87. Oh, did you all get this? Oh, you need a few more minutes? More seconds? Okay. Oh, sorry. Okay, so again, that's how that works. We could also use this getting coordinates. We could also do this using coordinates. Again, what you would use a very similar method. You would say this is 42. Using a 50-degree triangle with a hypotenuse of 42 feet, you would then find the x and the z coordinates. Then you'd have the coordinates of point C, and then you could construct a full force vector, or sorry, a full displacement vector for line AC. and the rest would fall into place. Fx over F, etc. Okay, and I think I will post these slides online after this, so if you don't quite have this, there you go. Okay, knowing the tension in cable AB is 1,425 newtons, determine the components of the force exerted on the plate at point B. So, in this one, notice I already have the, didn't we work through this one yesterday? Or one very similar to this?
Yeah, they use the same
The same
dimensions.
dimensions. Do you feel the need to work through this? I mean,
I got a question.
uh,
I just want to know how they got which angles to use.
in this one, I would not calculate any angles. I mean, you could, but it would make more sense just to directly calculate. Okay, let me just write out the steps.
Like basically, like can you draw like a free body diagram?
Uh-huh. Okay. Steps. 1. Get coordinates of points A and B. 2. Force will act from B to A. Thus, find vector BA. By subtracting coordinates of B, or actually coordinates of A from coordinates of B. Or other way around, actually. Subtracting A minus B. Final minus initial. What I mean by that is just, let's see. Vector AB is going to be equal to AX minus BX, comma AY minus BY, comma AZ minus BZ. Like so. Okay? So that's how we get vector AB. 3. Get lambda BA, or lambda AB. No, wait, AB, sorry. I keep getting those back and forth. Let me B. BA is equal to this because it's final minus initial. Vector BA is that. So lambda BA is going to be equal to simply BA over the magnitude of BA. BA over the magnitude of BA. Then once we have that, we simply say FAB or FBA. Derp. I really want to say BA for some reason. FBA is going to equal 1,425 newtons times lambda BA. And in that case, it's pretty much a plug and chug operation. Okay? That's all there is to it. Very, very similar to the problem we worked through yesterday. So again, I could even get vector BA really quickly here, because we know that that point A has coordinates. Let's say that's going to be 0, 360. No, 0, 600. 0, 600, comma 360. And B is going to have coordinates, so yeah, 0, 600, comma 360. And B is going to have coordinates 900, comma 0, comma 0. So it has no y. It has 0 height in the y and a 0 distance in the x, or 0 distance in the z. So then BA, again, final minus initial, is going to be 0 minus 900, so negative 900, comma 600 minus 0, so positive 600, 360 minus 0, just 360. All of that in millimeters. And then you find the unit vector, you work through it, and that's all there is to it. Questions on that? Okay. That's the general method there. BA. The reason we did BA is because the force is we're asking at the force exerted. We're asking for the force exerted by the cable on the plate at point B. So it's going to be going from B to A. It's pulling. It's going from B to A. Okay, this was a fun one. Ew. Let's think about this for a second. The boom OA carries a load P and is supported by 2 cables as shown. Knowing that the tension in cable AB is 1,830 pounds, and that the resultant of the load P and of the forces exerted at A by the 2, knowing that the tension in cable AB is 183 pounds, okay, we got that, tension in cable AB, and that the resultant of the load P and of the forces exerted at A by the 2 cables must be directed along OA, determine the cable, the tension in cable AC. Now, this looks terrifying, but it's actually not as bad as you might think. Okay. So I know the following. I know a few things. First, I'm going to have, I need a way of noting, I need a notation system that I can use consistently to sort of simplify this and make very clear what I'm finding. So what I'm going to do is, I'm going to have perhaps just, I'll have FABX, FABY, FABZ, that kind of thing. So I know that FAB, or the magnitude of FAB is 183 pounds. So I can, since I know the dimensions of FAB, I know the dimensions of the vector, etc., I can find the, will have no trouble finding the components, the X, Y, Z components of that force. Now let's see here. I know, what else do I know? I know that the Z component of this force must balance the Z component of this force. So I think this is basically what I know. I know that FABX must be equal to FACX. Well, equal and opposite anyway. Negative, you might say. See, this force P is purely vertical. This force OA is purely along the x-axis. Oh, did I write that down wrong? Yeah, I did. That should say Z. That should be FABZ equals FACZ. So the Z component of the force AB must be equal to the Z component of force AC. They have to be in balance. There is nothing else to balance them. So clearly they must be equal.
Is it keeping the rod straight and it's not moving to one side or the other?
This is a statics problem. Yes, it's not moving whatsoever. Yes.
Oh, sorry. Could you kind of say that it's in partial equilibrium?
No, it's in complete equilibrium.
Right. But doesn't the resultant go along the way, though? So.
No, because this thing is going to have a force, and we could calculate that.
Okay.
What this is just saying is that this rod will not carry any X or Z directional, sorry, it will not carry any Z or Y directional force. It
Right.
will only carry, the other force. It'll only carry X force.
Okay.
So, let's consider that then. So let's look into this and see what we can find. Here, what I'm going to say is I'm going to apply this relationship here. Now, let's see. I need to know the length of AB. So, of line AB, not the force AB, but the line AB. Actually, let me do, yeah, AB will work fine. The magnitude of line AB, well, this is a distance formula. 48 squared plus 24 squared plus 29 squared. I'm trying to find the length of line AB, and this comes to 48 squared plus 24 squared plus 29 squared. And that is exactly 61 inches. And then I will also need the length of AC. So the magnitude of AC is going to be equal to the square root of, so this is just the Pythagorean again, 25 squared plus 36 squared plus 48 squared. And that comes to plus 25 squared plus 36 squared, and that comes to exactly 65 inches. So the first thing I'm going to do is apply equilibrium in the z direction. So sum of forces in the z direction is going to be equal to, well, let's see. I'm going to have the FAC z, but minus. Actually, I should probably make that, that should just be positive, I think. There we go. That makes more sense with this math. Plus FABZ, like shown, or like so. Okay? And so we're trying to find the tension in cable AC. Then, the question is, okay, if you want to know why this, the question is why is the Z component negative here? Well, we're looking at the tension at point A, so it is clearly pulling point A in the negative Z direction. Okay? Now, there is a very simple, for these three-dimensional problems, there's another way I can do this. If I want to know the X component of the force here, observe what I'm doing here. Now let me make that equal sign a little neater. This is equal to, oh, and of course this is equal to 0. Negative, would you believe me if I said the problem is almost complete? It actually is. Negative, let's see, 24 inches over 61 inches times FAC. Plus, let's see, actually, no, sorry, this should be 36 inches. If I'm going to have the FAC first, then I got to do, then I need to make this 36 inches. 36 inches over 65 inches. The problem is still almost complete. Negative 36 inches over 65 inches. In fact, let me just label these. 65 inches and 61 inches for this. Plus FAB times 24 inches over 61 inches. In other words, I am multiplying by a fraction from its geometry. I am multiplying by the z component over the overall length. I'm multiplying the force by the length in the z direction over the total length, and that will actually give me the z component of the force. And all of this is equal to 0. And so then, negative 36 over, let's see. So this then is, well, I can just say 36 over 65 FAC is equal to FAB times 24 over 61. And then FAC is equal to, well, FAB is actually, as we found earlier, 183 pounds times 24 over 61, which is 183 times 24 over 61, which is 72 pounds. So FAC, therefore, is going to be 72 pounds times 65 over 36. Just solving this, imagine just this equals this. 72 times 65 over 36, and exactly 130 pounds. Huh? Exactly, yes. And that's how you solve problem 2.97. It's not actually very long. Simple, right? Easy, right? Yeah. hmm Yes, the hardest problem is definitely visualizing it. Just trying to tease out the system and figure out which components are where and things like that. But some of that comes down to experience. So again, let me follow through with this. All I'm doing is apply. If you want to find, we see something here, something very powerful. If I have a three-dimensional system, if I have a force along a known geometry, I can take, if I want to know a component of that force, I can multiply the magnitude of that force times the component, the length of the component I'm interested over the overall length. So look, basically what was this? Or look here, what is this? I have FAB, that's the size of the force, the magnitude of the overall magnitude of the entire force. I multiplied by the distance of the cable in the x over the total distance. So this is how I kind of visualize this. Do you remember, do y'all remember like dimensional analysis from chemistry? Remember where you would multiply, if I want to go from like, you saw this a lot in chemistry class, where if I want to go from like, oh, I don't know, like, let's say I want to go from 182 grams times 1 mole over 42 grams or something, you know, that kind of thing. That's dimensional analysis. I like dimensional analysis. I think like that a lot. And so I kind of interpret this through the lens of dimensional analysis sometimes. In the way I kind of visualize it is I think of I sort of think of like a hypotenuse as a pseudo unit and an x component as a pseudo unit. And so this overall force is a hypotenuse unit, quote unquote. I know that's not properly true. It's a weird way to visualize it, but I think it helps me. So when I visualize finding the x component, I visualize multiplying by a hypotenuse by an x over a I cannot talk today. Multiplying a hypotenuse by an x over a hypotenuse. Tongue twisters today. Then the hypotenuses cancel. Exactly. So, I don't know. Maybe that's confusing and you don't want to visualize things that way. That's fine. Maybe I'm just weird. Okay.
It's kind of the same thing as multiplying by components of lambda, right?
Yeah, essentially, yes. That's all it is. Different ways to do the same thing. All right, other questions? Okay. With that, I think we'll move on to the theory for today. So we do have quite a bit of ground to cover. Namely, in the beer vector mechanics book, we're going to cover from about 3.1 to 3.6 is my goal today. Okay. So the chapter 3 starts by talking about some principles. Chapter 3 starts by talking about a few basic principles that I'll touch on briefly. I will mention 3.2 and 3.3, what these are. External versus internal forces. I'm just going to briefly touch on these. They're not really, they're pretty obvious, not necessarily worth a great deal of exploration. External versus internal forces. This one is fairly straightforward. External, maybe I'll put this in the next line actually. External arise from a force, a contact force most likely, applied at the surface of a body. Internal internal arise from the bulk of the material, from forces applied to the bulk of the material. So this one is simple, like just like pushing, pulling, etc. From forces applied through the bulk of the material. Through the bulk of the material. Of the material. So you can have things like pressure, electrical force, electrical attraction, electrical Coulomb attraction. And the big one that we're going to talk about, of course, is gravity. Gravity is the main one. So this, does that bother anyone calling gravity an internal force? Isn't that kind of weird? Yeah, because gravity clearly originates from outside the body, but so that's where it really starts to get really kind of strange. The reason we call it an internal force is that when we draw a free body diagram, okay. Yeah, exactly. It's because of the center of mass. Exactly. What we say when we draw a gravity vector. When I have a drawing of a free body diagram of somebody, and I draw a gravity vector, okay? So I have a free body diagram. This is weight, normal force, that you're familiar with. What does this weight vector, what does this gravity vector represent fundamentally? Now, gravity doesn't work on on single objects. It's not how gravity actually works. When I draw the gravity vector here, what I'm really saying is this is the vector sum of quadrillions upon quintillions of individual gravitational attractions. Every atom in this person's body, or in whatever object I am modeling, so every single atom, every single proton, every single neutron is being pulled in an individual tiny force vector to every single other proton, neutron, and electron of the entire bulk of the Earth, and in fact every atom in the universe. But usually we're not concerned about extraterran That's a fancy word. We're not concerned with any other gravity except the pull of the Earth downward because everything else is negligible in most cases. But so when we draw this gravity vector, what we're really saying is we're talking about a vector sum. When you take those individual, innumerable, infinite number of tiny little force vectors, one atom pulling, like, so for example, you know, if I look at my hand, there is somewhere in the palm of my hand, there is one atom, and that atom is experiencing a tiny, 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 tiny force vector pulling it toward another atom somewhere in the middle of the Australian outback, right? That's true. There is a tiny, 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 tiny little gravitational force vector pulling it that way. It is so small you could never even possibly hope to measure it, but it's there. And when I say my weight, what I'm really talking about is the combined average vector of all of the atoms in my body being pulled to all of the atoms of the Earth all put together. So that's what we call weight. So anyway. But that is why we call it an internal force, because yes, it is sort of, it only happens if there's an external object, but it's originating through a bulk interaction of all the materials, of all the atoms in a body. So, etc. Pressure is obvious, although we won't deal with that. We won't. That's kind of obvious why that's an internal one. Electric force, same idea as gravity. If you have a charged object, etc., etc., etc. So questions in that principle, fairly straightforward. Oh yes, and of course, gravity vector. The gravity force vector acts through an object's center of mass. And when we get to the unit on centroids, we will actually learn how to calculate that a little better. Through an object's center of mass. All right. Other questions? Okay, fairly straightforward. Then the book also talks about the principle of transmissibility. We've talked about that a little bit, but I want to mention it here. I want to actually introduce it in the lecture a bit. Principle of transmissibility. What does this mean? So I'm going to draw one of my favorite objects to draw, a potato. Oh, I don't have brown here. Ugh. Oh well, it'll have to be a green potato. So I have a potato or perhaps a shrubbery. All this means is this is an arbitrary object. I don't care what shape it is, this is just an arbitrary object. It has a center of mass here. All right, I am going to apply a force to this object, again at an arbitrary point. Let's use red. So let's say this is a two-dimensional object, for instance, but the same would apply in 3D. So I apply force F on the surface of the object, at the edge. This will cause it to do two things. It'll cause the object to tend to move in this direction, right? Let's assume this thing is just floating in space. It's just floating in the vacuum of space. There's no other forces on it except the force that I'm applying. So if I come up with my spacesuit and poke this thing with a stick, that would be the most wasteful NASA experiment ever. Spent 200 million just to put someone in space and poke something with a stick. Anyway, that's why my NASA funding proposals haven't been approved. Anyway, so we have this. So we have this arbitrary object floating in the vacuum of space. I come along and I apply a force to it here. So this causes two tendencies. One, it causes the object to tend to move in the direction of the force. So it will want to cause an acceleration in this direction. And it will also want to cause a rotation about the center of mass, correct? The only way this will not tend to cause a rotation is if what? It's directly through the center of mass. Let me, now for objects that are nailed down, it would be acting through the rotation point. I can illustrate this concept here. So what I'm going to do is I'm going to go up to the door of the classroom here, and I'm going to open it. And now we can see, well, you can lean out the door. I can apply my finger. Clearly, you can open a door. It does not take much force to open a door. But the amount of force required to open a door varies depending on where you apply your force. If I apply the force far from the hinge or from the line of rotation, it takes very little force. But as I move closer and closer and closer and closer, I will find that it requires more and more and more force. Now I can open it if I put my finger right near the edge, but it's quite a bit of effort. Of course, if I apply the force directly on the hinge, I basically can't do it. Because, and the reason for that fundamentally is that a force applied to an object will, in order to cause rotation, you need two things. You need both a force and a moment arm, which is what we saw, we discussed that briefly yesterday. But if we don't have one or the other, we won't get a rotation. So if I apply a force if I apply a force right at the hinge, which in this case would be the equivalent to the center of mass for this object, it will not generate any moment, it will not cause rotation. But anyway, we'll get more into that in a bit. So let's go back to the principle of transmissibility. So we realize that a force applied to an object will cause two things. Cause a tendency for two things. That looks awful. Forces cause an object to A, translate, which means basically the center of mass moves. That's how I would define translation. Well, at least physics translation, not language translation. The center of mass moves. So they cause an object to translate, and they also cause an object to rotate. Movement about center of mass. So rotation about the center of mass. Now, let's see. So a particular force and a particular arrangement will cause an object to behave, will cause different behavior for an object. For example, if I increase or decrease the magnitude of the force, it will translate to a different degree. If I change the angle, it will change things as well. If I increase the distance from the center of mass, it will cause a greater tendency to rotate. However, there is one way we can change a force that it will remain the same, and that's the principle of transmissibility. What the principle of transmissibility means is that I can move a force anywhere along its line of action, and it will still cause the same tendency to translate and rotate in an object. So, I can move a force anywhere along its line of action, along its line of action, and it will exhibit the same tendency to translate and rotate. To rotate. So what does that mean? how can I move this force along its line of action? Well, assuming this was like an arbitrary plate, just like an arbitrary two-dimensional shape, a very thin kind of weirdly cut plate, I could do a couple things. One, I could go and apply, as I have it shown right here, I'm pushing on the edge. I could bring the force over here, attach it to a rope, and pull on it. And it would exhibit the exact same tendency to translate and rotate. I could, if I was so inclined, I could put a nail here and nail into the board and pull on it here, or I could push here, etc., etc., etc. Any method I want to do, I can move this thing anywhere along its line of action, but as long as I don't change the magnitude of the force or its direction, and I keep it along the same line of action, I can move it anywhere along there, and it will exhibit the same behavior. And the point of this is that the reason we're covering this is that this can be important for calculating moments, which we will see briefly. All right, questions on the principle of transmissibility? Yes.
To what they call in physics path independent.
The question is this similar to the principle in physics called path independence? I would say not quite. Path independence is talking more about energy. What that's saying is in many types of energy problems, if there is no work done in a system and no energy is entering or leaving the system, it doesn't matter whether you are, it doesn't matter what path you take to do there. So for example, you've probably at some point in your career, your academic careers, seen the famous roller coaster problem, where I say there's a roller coaster at the top of the hill here, with a height here, I release it from rest or with a certain velocity. It goes through a bunch of arbitrary loops, and then up on this end, it's at a certain height here. What's its velocity here? Well, not necessarily. It doesn't have to be zero, no. The only way it's zero is if it's at the exact same height as here. But if it's not, it's going to have some other velocity. Now, yes, in the real actual case, they will put brakes on it and make it stop. But that's an example. A brake is a non-conservative force. It's taking energy from the system. If this is a true zero loss track, like a no friction track, no air resistance, etc., it doesn't matter what path it takes. It doesn't matter whatsoever. I can put it through 1,000 loops. I can put it through no loops. It doesn't matter whatsoever. As long as no energy is lost, it's path independent. All I need to know is the initial position and the final position, and I can find its velocity at that point. Now, the real world gets more complicated. If you actually want to build a roller coaster, I would not recommend assuming a frictionless track. You're going to kill somebody. But anyway, for simple physics, it works. And for actually for designing certain things, path-independent assumptions are fine. All right, so other questions? Okay. Moving right along. Okay. So we need to talk about the vector product or the cross product next. So, what do y'all know about cross products? They're what? J is negative, yes. Well, sort of. The J is negative, yes. Sort of. That's really. Okay. So let's see. How can we say this? Cross product or vector product? Or a vector product? Now, there are many ways to interpret the vector product and describe what it is, etc. But we'll look at how to calculate it, and we'll look at some of the properties of it. But anyway, the most useful thing that we're going to do with it is calculating moments. Okay, so here, if I were to define it, here is one way to define it. We can define it in terms of three-dimensional vectors, or we can also define it in terms of two-dimensional vectors on a plane. So let's start with that one first, like they do in section 3.4 in the Bioreactor Mechanics book. So simple explanation. If I have two forces, force A and force B, And these are actually, you know what? Maybe I'll draw some axes first. I think that might help a little bit. Sorry. So if this is x, this is z, and this is y. Say I have two forces. Um, oh, dang it. In color. So I have force A and B are in the xz plane. Forces A and B are in the xz plane. They don't have to be. They can be in any arbitrary plane, but let's for simplicity say they're in the xz plane. So say I have force A and I have force B, and they are separated by an angle theta. Okay? Well, I can then say the cross product, let's see, is going to simply be, well, you'll see here. Let me give maybe a green vector here. It's going to be perpendicular to both of them. It's going to be mutually perpendicular. So this would be A cross B, like this. And so maybe I'll just let that equal, oh, I don't know, C. And these are both vectors, vector A, vector B. And then the magnitude of vector, and that's C is also a vector. The reason it's called a vector product is because the resultant is a vector. After you complete the operation, your result is a vector. So the magnitude of C, if I want to know the magnitude of C, well, first of all, I know the direction is always going to be mutually perpendicular to A and B. So notice this. This works by the right-hand rule, if you remember that. You can have the plane represented by these two forces, and the now you can think of it with a curling hand, or I actually like to use like a flat hand, where I would draw like a okay, I am terrible at drawing human hands, so I warn you in advance. Here's my human hand.
So would that be B cross A?
Yeah. This is where you learn. I've never been to art school. Okay. So, in other words, I could have A here. These are the fingers outstretched. B and AB, A cross B, out of palm. That makes sense? Did I draw a left hand? Oh, derp. Depends on your Wait, does it depend on your interpretation? No, that's, yeah, I'm so bad at drawing, I've confused myself.
Well, it depends on, it's a fist.
Maybe it's a fist.
Then yeah, it's
It was meant to be the palm side.
yeah, that's a lemon. If it was a fist, it'd be.
Oh, okay. You know what? I don't like this. This is bad. Let me just erase the evidence. Oh no, this is recording. Crap. Okay. So let me draw another potato hand with like a comically oversized thumb. Okay, so this is now our right hand. So this would be A cross B. This would be A, and this would be B. Happy now? Okay. So again, out of palm, you can use the right hand rule. See your book for actual decent drawings. I don't know what kind of weird poisonous spider or something that hand was bitten by, but oh man. Yes.
Oh no, I wasn't questioning the right whatsoever. I know you probably can't draw this, but what's the distance?
You don't have faith in my abilities?
In physics one, what we did was, I understand the right hand rule, but what you could do is like the middle finger points towards one direction, whereas the index finger points another direction.
Yeah, you can use methods for fingers pointing different directions and this, that, and the other thing, but I can draw a hand, sort of, so I'll do that one. Okay. Yeah, there's a lot of different ways to do it. So fundamentally, let's go back to this. The magnitude of C, though, is going to be equal to the magnitude of A times the magnitude of B times the sine of theta. So that's one way to describe the cross product operation. So its direction is defined by the right-hand rule, and its magnitude is the magnitude of A times the magnitude of B times the sine of the angle between them. Okay? All right, so that's one way to visualize it. However, usually we're doing this in terms of rectangular components, so I'm going to look at something a little different, something a little more useful. You can do it this way, but I don't like breaking out the right-hand rule. This is not physics 2, so let's ignore that. Okay, you got this? Okay. I think you'll find that the rectangular vector method the rectangular component method is going to be a lot more useful generally. Okay, so cross products via rectangular components, vector components. Cross products via rectangular vector coordinates, or components coordinates, close enough, same thing, sort of, not really. Via rectangular vector components. So let's see, say we have, now I'm not going to do this in terms of units just yet. Let's just say I have vector A. This is a review from math. Technically, you should all know how to do this by now. But okay. So let's just say I'm just going to create 3 arbitrary vectors, 3, -2, 1. Did I say 3 arbitrary vectors? I meant 2. -2, 4, I don't know, 5. Or maybe. Oh, let's do 2 here. Okay. So, how do I find the cross product? The first thing I'm going to do is create a little table with I, J, and K. So I'm going to have A, B, and then components I, J, and K. So I'm going to put 3, -2, 1, -2, 4, 2. So the actual cross product is going to be equal, okay, for each step of these, I'm going to cover up, if I want the I, basically, if I was doing this on the board, I would actually show covering this up with my hand, but I can't really do that on a screen. So when you calculate the I component of the cross product, you ignore the I part of this table. So it's always this way minus this way, right? Remember that? this minus this. That's the determinant calculation. So it's going to be negative 2 times 2 minus 4 times 1, all of that times the vector I, the unit vector I. Now, for j, I'm going to do 3 minus 2 times, or minus negative 2 times 1. However, I need to remember to put a minus component on the j. So whatever I get from the j, I'm going to put a minus. So 3 times 2 minus negative 2 times 1, j, plus, and now I'm going to use I'm getting the k component, so I'm going to cover up this k. So this minus this. So 3 times 4 minus negative 2 times negative 2. And you quickly realize in calculating these, the devil is always in the negatives. But that's okay. We know how to do math. We know, in this class, we all know Algebra 1. Actually, this is probably pre-algebra. So anyway, this is going to be negative 4 minus 4, so negative 8i, right? Negative 8i. And then, let's see, 3 times 2 is 6, plus, so this is plus 2, right? So the whole thing comes to negative 8. Negative 8j. And then 3 times 4 is 12. Okay, we got 3 negatives here. Oh, minus, that's going to be negative 4. So that all comes to positive 8, right? Assuming I'm mathing correctly. What? No, actually, I did not. Wow, that's incredible. I actually did not intend that. I don't have that written anywhere. That was, huh. It'd be more impressive if it was all like positive 8 or something. But, huh. Clearly the computer is haunted. That's the rational explanation. That's the rational scientific explanation. Okay, anyway, and that is going to be A cross B. Now we're going to have one more thing, and then we can go to break. I want to introduce where we actually use moments, or so where we actually use the cross product to find three-dimensional moments. All right, questions on the basics of finding a cross product. Okay, again, hopefully you've all seen this many times before. I just wanted to give a refresher. All right, finding a moment about a point using cross products. Finding a moment about a point. And do I need to cover Varignon's principle? Yes, we also need to go over Varignon's principle. Okay. Finding a moment about a point. So, finding a moment about a point. So, say I have a point, just an arbitrary point, say O. I have a point A, and between them is vector R. Vector R. And then I have a force vector, acting through point A. So, the moment vector of force F about point O is all it is R cross F. That's all there is to it. So, if you know the force, so the first thing is going to be to find the force vector. Then you want to get the vector from the point you're interested in the moment about to any point along the force's line of action. It can be here, or I could also take the point here. It can be anywhere along the force's line of action.
Where's that line of action?
The line of action would be like this way, etc.
What?
The force's line of action?
Yeah. Oh, it's just pointing along the.
It's pointing some direction, yeah. So the force's line of action would be like if I can draw a straight line. Yes.
That's the moment about O, right?
Yes, this is the moment about O. So if it helps, I'll draw a little O here. Moment O. So yeah, that's it. That's how to find the moment about a point. And there are two kinds of problems we're going to look at when finding moments about points. Huh? Difference between moment and torque. That is a classic question and something students always ask. And I'm sure if you dig down into the etymology of the word moment, you can probably find a really good explanation for that. Generally, just know in engineering we use the term moment. Physicists sometimes like the word torque. We like moment, often because we talk about internal moments, internal bending moments, and things like that. It has to deal with, remember, like first moment, second moment, area, things like that. We'll look at calculating later. So as far as why you call it that, you have to get into some of the subtleties of moment versus torque to really realize it. But just for now, just accept it on fact. You're no longer talking about torques. You are now for here and evermore talking about moments. So deal with it.
So that moment's going into the board.
Yes, this moment would actually be going, well, actually, wait a minute. Let me apply the right hand. Well, yeah, actually, yes. This moment is going into the board from your perspective. Yes, this moment is absolutely going into the board. Because if I apply the right hand rule with my curling fingers, the vector of my thumb would point into the board. Absolutely. So, other questions about this? Then I just want to introduce Varignon's principle, which we will use later on. Okay, I need to keep this and I put another slide in here. We actually ran through all my slides. So let me just call this 8.5. Oh, just a second. Okay. Oh, what happened? Oh yeah. Uh-oh. I screwed up. Sorry. Oh, there we go. That'll work. Uh, so, the last thing of theory I need to introduce is called Varignon's principle. So, I don't want a red one. Varignon. Varignon's theorem. So this is Varignon's. That's how you pronounce this, Varignon. If you does anyone speak French? Am I getting that right?
Yeah, you got the accent
Okay. Okay. If you are really if you're out from way in the Texas sticks and you want to sound like a hillbilly, you can call it. That's Varignon's theory. Varignon. That's Varignon's theory right there. I'm not calling.
Drop the last N. They always drop the last letter.
Oh yeah.
No.
Varignon. Okay, gotcha. So that's actually Varignon. Okay. Cool. All right. But let's not worry about this. This is not French class. But anyway. Now, so Varignon's theorem. The basic idea here. This is a very simple thing, actually. A force. Or actually, let me say. I always like to restate these in my own words. If multiple forces act through a single point, a single point, the vector sum of those forces, will produce the same moments about all points. produce the same moments about all points. In other words, they are interchangeable. So, what do I mean by this? Let's go back to the previous example. Let me draw something very similar. So I have point O, point A, and let me do a little green here for the R. The R here. And let's say I have several forces acting through point A. F1, F2, F3. Just arbitrary forces. Well, instead of doing that, let's say I come along and say, you know what? Let's just say I don't know, Fs for some perhaps is F1, and these are all vectors, plus F2 plus F3. And then I could just replace these with Fs. This will cause the same behavior, the same moment about point O, as this combined force will cause the same moment about O as all of the individual ones. So we could add up we could find the moments of each individual one and then add up the resulting moment. Or we could add up the forces and then find the moment of the combined force. This works both ways. This works both ways. Confined moments you can find moments of either combined or separated forces. Separated forces, whichever is convenient. Whichever is convenient. Now, so where this is really useful is especially for two-dimensional problems. So what you can do is, when I say separate forces, that includes components. So in many two-dimensional problems, it's very beneficial to simply take the moments of components, because with those, it's very easy to calculate perpendicular distances. So we will see that coming up in a bit. So Varignon's theorem is Varignon's theorem. Varignon's theorem is a very useful tool for calculating complex systems of moments, which we will see when we come back from the break. All right, any questions? All right, if there are none, we'll take a short break. We'll come back and look through some example problems from the book. All right, thank you.